Hello guys, welcome back to my channel HK Official. Today I'm there with the part 3 of this chapter, which is Unit 1 Wave Optics in Engineering Physics. In this video, I'll be covering derivation of interference in wedge-shaped film, then fringe width, then some numericals on fringe width and interference due to thin film, and also we will see at last the colors in thin film. So let's get started. The first topic which we are going to cover is the interference due to non-uniform thickness thin film. We can also call it as wedge-shaped thin film. In the previous video, I covered the very important topic of the chapter, that is interference due to thin film. If you have not watched it yet, please watch that video first and then come to the next. So, let's get started with this. This is the diagram for interference due to wedge-shaped film, or we can call it as non-uniform thickness thin film. So in this diagram, you can see the angle theta is inclined to the plane. That is nothing but the wedge-shaped film. So here the same thing happens, that is SA, which is the ray of monochromatic light, it get incident at the angle I to the normal, and part of the light get reflected along AE and part of light get refracted along AB. Similar method which we had seen in our thin film interference, same we are following over here. Just an addition is that the angle theta. So here also you can see again from point B what happens, it get reflected along BC, then it emerged out. This interference caused is due to the path difference between two rays. So let me say that we are not going to derive this path difference because it is not in our syllabus. We have direct formula and we have to calculate the condition of maxima and minima. So if you remember what was the path difference in interference due to thin film, then you are definitely going to rock this. Here I have written the consideration part with the diagram. You can copy this, and the same I have explained you now, that SA is the ray of monochromatic light incident at angle I to normal. Part of the light get reflected along AE and part of light get refracted along AB. Again from point B it get reflected along BC, then it emerged out, and interference caused due to path difference between two rays. If you remember, it is the same as that of thin film. Nothing is changed. Here what is the formula? That is delta. What is delta here? It is the path difference. It is 2 mu t cos r plus theta plus minus lambda by 2. If you remember the interference due to thin film, their path difference was 2 mu t cos r plus minus lambda by 2. Here in wedge-shaped film, an angle theta is inclined, so just add theta in cos. That is the final output which you are going to get in total path difference. So after drawing the diagram, you have to come towards this formula directly. You don't have to derive this formula, remember. Okay, so what is that? Delta is equal to 2 mu t cos r plus theta plus minus lambda by 2. I hope you know why plus minus lambda by 2 is added and subtracted. It is because of Stokes' law. Now here we come to the condition of maxima. I have given you all the things which you have to do step by step, and the same you have to cover in your exam also. Okay, so what is the condition of maxima? The same as which we have seen in interference in thin film. Delta is equal to 2n lambda by 2, or you can take it as n lambda, which is the condition of maxima. Okay, you have to consider that. Now what is delta? Path difference which we have known for this wedge-shaped film. It is nothing but 2 mu t cos r plus theta plus minus lambda by 2. So just equate these both. So we will get 2 mu t cos r plus theta plus minus lambda by 2 equal to 2n lambda by 2. Just simplify, you have to keep 2 mu t cos r plus theta on the left hand side, and whatever is there you have to keep it on right hand side. Simple. So here what will happen, this plus minus lambda by 2, which is because of Stokes' law, it will go towards the right hand side, and what it will become? It will become 2 mu t cos r plus theta is equal to 2n lambda by 2 plus minus lambda by 2, and the final output will be 2n plus minus 1 into lambda by 2. Simple. You have to just rearrange. What you have to remember? Just you have to remember what is the value of delta for condition of maxima. That is 2n lambda by 2. Just equate it and you will get the condition of maxima. Hope you felt it very simple. Let's go towards condition of minima. What is condition of minima? It is nothing but delta is equal to 2n plus minus 1 into lambda by 2. The same which we have seen in interference due to thin film. I am saying it again and again. If you have not seriously watched that video of mine, that is interference due to thin film, please watch that. You will be getting this concept very simple. Now here, as delta is 2 mu t cos r plus theta plus minus lambda by 2, just equate this both, which is the condition of minima. What it is? 2n plus minus 1 into lambda by 2. As I told you, you have to just keep 2 mu t cos r plus theta to the left hand side, and whatever the thing is there, you have to keep it on the right hand side. So here, if you simplify, I will multiply lambda by 2 into 2n plus minus 1. So what I will get in simplified format, I will get 2n lambda by 2 plus minus lambda by 2, and the one which was due to Stokes law, that also would be added, plus minus lambda by 2. As these both are same, this would be cancelled out, and 2 and 2 will be cancelled out. So what will be the condition of minima finally for us? It would be 2 mu t cos r plus theta is equal to n lambda. That is the condition of minima. Super simple. Now let's go to for transmitted light. So as we have calculated for condition of maxima, then minima, so we have to consider for this also, that is transmitted light. It is again very simple. You just have to remove the Stokes law, that is plus minus lambda by 2, and you have to do the same thing that we have done before. So as light is transmitted, no phase change occur. Why? Stokes law is applied because of phase change. But here we are no phase change occur in transmitted medium, so we will not add that Stokes law component, that is plus minus lambda by 2. So here what will be our condition of maxima? For all things, remember what is the condition of maxima? It is 2n lambda by 2. But for here, what you have to do, you don't have to add plus minus lambda by 2. Just consider 2 mu t cos r plus theta. Equate it with the condition of maxima, that is 2n lambda by 2. Then simplify. Nothing is there to simplify. Just cancel 2 and you will get the final condition of maxima, that is 2 mu t cos r plus theta is equal to n lambda. If you have considered before the condition of minima, which was there in wedge-shaped film, now it is the condition of maxima in transmitted light, same as in thin film. Now let's go to condition of minima of the same condition. Delta is equal to 2n plus minus 1 into lambda. Just don't add Stokes law component, plus minus lambda by 2. Just don't consider it. Say take delta is equal to 2 mu t cos r plus theta is equal to 2n plus minus 1 into lambda by 2. The same carry forwarded in the third line, and that is your condition of minima. I hope you considered it very simple. So this was nothing but the derivation for your interference due to non-uniform thickness thin film, or you can take it as wedge-shaped film. Just go step by step diagram, then take some consideration part, condition of maxima, condition of minima, and then if asked for transmitted light, then write for transmitted light. Otherwise you will get full 6 or 7 marks as per your question. Okay, now let's go towards fringe width. I hope we are familiar with this concept from our 12th standard, but here only simple we have to consider the formula. No derivation, no nothing, just consider the formula, and the most expected thing in fringe width is the numerical. So let us first see the formula and then we will go to the numerical. Here fringe width is nothing but the difference between either two bright bands or dark bands. I hope you all are remembering all the things in which we have studied in 12th standard. Okay, what is fringe width? It is the difference between either two bright bands or dark bands. Okay. What is the formula for fringe width? Remember, fringe width is denoted by beta. Okay, so this beta is equal to lambda upon 2 mu sine theta. Lambda is nothing but wavelength, mu is the refractive index, and sine theta. Okay. Now this is small derivation, which not derivation, just a simplified version. For a small angle we cannot, if we consider theta in the place of sine theta, then also it is well considered. In most of our examples also in numericals, we don't consider sine theta, we consider theta in the place of that. So for small angle, sine theta is theta. So our formula is simplified to the format of beta is equal to lambda upon 2 mu theta. Okay, here beta is nothing but fringe width, lambda is wavelength, mu is refractive index, and theta is nothing but the angle of non-uniformness or angle of wedge we can consider. So let us see a numerical on fringe weight, and don't feel like that I'm taking any of the numerical. These are the PYQs which have already came in our in-sem examination. So focus on the numerical. You will get the full concept over here. This is PYQ number 1. A wedge-shaped air film having an angle of 40 seconds. Now we'll be considering why this angle is given in seconds format. So we have to consider this and we have to convert it into radian, which I have given in the note below. So, a wedge-shaped air film having an angle of 40 seconds is illuminated by monochromatic light, and fringes are observed vertically through a microscope. The distance measured between consecutive bright fringes is 0.12 centimeter. Calculate the wavelength of light used. Here you have to note that if you have any book with you, please write this formula. It is very important in your numericals. 1 radian is equal to 180 by pi into 3600 seconds. But most of the time we are going to use the second one, that is x seconds is equal to x upon 3600 into pi by 180 radian. For example, over here we have given 40 seconds. So what we will consider, 40 seconds is equal to 40 upon 3600 into pi upon 180. So we will get into the radian format. Easy. Let's go towards the solution. So here is the solution. What we have given is with the theta, which is 40 seconds, beta, which is the fringe width, it is 0.12 centimeter, mu is 1 for air, that we have to consider. So here theta will become what I have told you in the note format before, which we have to convert it into radian. Remember this step, okay? So theta will be equal to 40 upon 3600 into pi by 180. After calculations, you will get the answer, that is 1.9 into 10 raised to minus 4. This is in the format of radian, okay? Now what is our fringe width formula? It is beta is equal to lambda upon 2 mu sine theta. Now as I have told you, we will consider sine theta as theta in most of the cases, or I can say in mainly of all the cases, because as the angle is small, we can consider theta as well in the place of it. So here we have to calculate what is the wavelength. So we will rearrange the formula and we will get lambda is equal to 2 mu theta into beta. So here after putting all the values, after using your calci and all, you can get the lambda as 4.56 into 10 raised to minus 5 centimeter. So I have taken it from the centimeter only. You can take it in SI unit format also in meter by converting it. But at the end, you if you write wavelength like thing in Armstrong, it looks better. So lambda is 4560 Armstrong. So that is the final answer. These are the super easy numerical for 6 to 7 marks. Just you have to do this thing. Keep the formula in your mind. Keep this calculation for radian and conversion of radian seconds. Just you have to remember these two things and you will be easily going towards the solution. Okay. Now I have also kept a numerical on one thin film. Okay. So let us consider for that also. So that is also a PYQ number 2 and it was asked in May 2016 in some paper. A parallel beam of light 622 nanometer incident on a glass plate of refractive index 1.5 such that angle of refraction into the plate is 60 degree. Calculate the smallest thickness of the plate which will appear dark by reflection. Which will appear dark for reflection is giving you the hint. What would be the hint? Yes, you are right. Condition for minima. So in this numerical, we have to calculate condition of minima. So that is the hint for getting us the formula. Let's go towards the solution. This is the solution. What you have to consider, the keyword over here is dark fringe. Lambda, that is wavelength, is given to us, that is 622 into 10 raised to minus 9 meter you have to take for nanometer. Here mu is the refractive index that is 1.5. R, that is the angle of reflection given to us. So we will consider it 60 degree. Sometimes the question will come in the format of angle of incidence. But in our formula, that is 2 mu t cos r is equal to n lambda. Remember, this is the condition of minima in interference due to thin film. Okay, so this is the formula for that, in which we have cos r. We don't have cos I. So we cannot consider I also, right? So here what will happen? You have to use Snell's law. That is sin I upon sin r is equal to mu, like that. Okay, but then from that you have to calculate R. Okay, so that you have to consider. But here in this numerical, R is given directly, so we will put it directly into the formula. So here 2 mu t cos r is equal to n lambda. I hope you remember from where it has came. It is the condition of minima. Keep 2 as it is. Mu is given 1.5. T, that is the thickness which we have to find out for that, and cos r, that is cos into 60 degree, which we have given, and is equal to 1. N we have kept as 1, and lambda is 622 into 10 raised to minus 9. As we have to calculate thickness, just modifying the formula, we will get the final output as 4.146 into 10 raised to minus 7 meter. I hope you understand it very well. It is the simplest formula which you have to consider. Mainly you will getting this condition of minima in your numerical. Still, if you get any bright format, so consider 2n plus minus 1 into lambda. Nothing else. Okay, so this is the format which you will get mainly in your examination. Practice such questions and yes, you will rock in the exam, I am sure. Now the last concept of today's video, that is colors in thin film. It is very simple and theoretical concept, and it is not that much important with as your exam point of view. It is just for your theoretical information. So sometimes it has asked, so out of 3 I'll give it 1 rating. If you are learning or reading your syllabus 3 times, then at one time you have to see the concept, so it would be better. So let us start with it. So the same thing I have written also here, that is delta is equal to 2 mu t cos r plus minus lambda by 2. Our main path difference formula. Just keep it. Here there are two conditions for excessive thin film and for thick film. So here the first I have considered, that is for excessively thin film, what would be the color pattern in thin film. Okay, so for excessively thin film, the name only indicates the thickness is approximately equal to 0. Okay, so I have written over there that T is approximately equal to 0, that is thickness, and if we put that T equal to 0 in our path difference formula, that is delta is equal to 2 mu t cos r plus minus lambda by 2, we will get to know delta is equal to plus minus lambda by 2. Simple. And we know that this plus minus lambda by 2 is the condition for minima. Now as it is the condition for minima, the film will appear dark. Super simple. If you have understood, it is very easy that if this plus minus lambda by 2 is the condition of minima, our film will appear dark. So for excessively thin film, our film will always appear dark. Okay. Now let us see what would happen for the thick film. The film of large thickness is illuminated by white light, then no interference pattern will be observed. So if there is a thick film and we give a white light to it for getting interference pattern, so it is impossible, because a film of large thickness is illuminated by white light, then we cannot see any interference pattern over it. Okay, in case of thick film, the condition of maxima at the given point is satisfied by large number of wavelengths and the point is bright. So for what condition? When the condition for maxima at the given point is satisfied. If the condition of maxima is satisfied, then and only there, and at that particular point we will get a bright point. Okay, now also for condition for minima, it is satisfied by other ways. Further, large number of wavelengths satisfy the condition of minima and the point is dark. The only simple thing which we have to take from this is that when the whatever wavelength is there, if the condition matches the condition of maxima, then there will be bright point, and when the condition matches with the condition of minima, there will be dark point. So this is the concept for thick film. This produce uniform illumination and colors will be sensibly white. Okay, uniform illumination will take place, bright dark. So we will consider it as a sensibly white point. Okay, so that is a simple consideration for thin film and thick film. So that is all about the colors in thin film. I hope you understood this video very well. I've tried to consider the numericals also, so that you will get to know what type of numericals are there in our exams. Okay, so I hope you understood it well, and in our further video in part 4, I will be considering engineering applications, in which we can see the testing of optical flatness, then anti-reflection coating, and then we will see diffraction, the types of diffraction. Hope you know what are the types of diffraction, Fresnel and Fraunhofer. Okay, then we have run of a diffraction due to single slit. All these further topics I am going to cover in part 4. If you are liking these videos, please like it and share with your friends, and don't forget to subscribe my channel. Let my channel go to all those who are getting difficulties in the topics which I cover. So thanks for watching for now, and wait for the part 4. If you have not seen the last videos, please see that, and thanks for watching for now.